The Arctic Ocean is the smallest ocean on Earth, covering roughly 5.4 million square miles. It is smaller than every other ocean. Yet, changes here carry more weight than in any other ocean. That isn't because of its size, but because of where it sits and how strongly it influences the planet around it. The Arctic Ocean lies at the planet's northern extreme, almost completely enclosed by land. For centuries, it remained isolated, locked under ice, and difficult to reach. That isolation allowed it to act as a stabilizer, a cold reservoir that helped balance temperatures, currents, and weather patterns far beyond the polar region. Today, that balance is shifting. Ice that once formed reliably is thinning and retreating. Open water now appears where solid ice used to dominate. Storms interact with the ocean in new ways. Routes that were blocked for most of history now open seasonally, exposing ships and coastlines to conditions that remain hard to predict. This ocean matters because changes here don't stay here. They spread outward fast. The Arctic Ocean influences atmospheric circulation, ocean currents, and seasonal weather across much of the northern hemisphere. When its behavior changes, the effects are felt far from the ice. For sailors, explorers, and modern crews, this has always been a difficult ocean to deal with. History shows repeated attempts to chart it, cross it, and use it, often with limited success. Even with satellites and modern forecasting, uncertainty remains a defining feature. This documentary looks at why the Arctic Ocean behaves the way it does, why it resisted understanding for so long, and why its transformation now carries global consequences. To understand why the world's smallest ocean matters most, we first need to understand what makes it fundamentally different from every other ocean on Earth. That begins with its geography. The Arctic Ocean is small by ocean standards, but its layout gives it influence far beyond its size. Unlike the Atlantic or Pacific, it is almost completely surrounded by land. North America, Greenland, and Eurasia form a ring around it, leaving only a few narrow connections to the rest of the world's oceans. This enclosure limits how water, heat, and ice move in and out, making the system highly sensitive to change. Much of the Arctic Ocean sits on broad continental shelves. Large areas, especially north of Siberia and Alaska, are shallow compared to other oceans. Shallow water warms faster, freezes differently, and responds quickly to shifts in wind and temperature. These shelves play a key role in how ice forms and breaks up each year. At the center lies a deeper basin divided by underwater ridges that influence circulation beneath the surface. These features guide slow-moving currents that are layered and difficult to observe. For a long time, their shape and behavior were poorly understood simply because ice made direct measurement difficult. The Arctic connects to the Atlantic mainly through the Greenland and Norwegian seas via narrow passages near Greenland, and to the Pacific through the narrow Bering Strait. These gateways act like narrow valves. Small changes in flow can alter temperature and salinity across wide areas of the ocean, affecting ice formation and stability far from the entry points. This combination of enclosure, shallow shelves, and restricted connections explains why the Arctic Ocean behaves differently from every other ocean. Energy tends to remain trapped here, allowing changes to build instead of fading away. For centuries, this structure slowed exploration and limited understanding. Even today, it remains one of the least directly observed ocean systems on Earth. The geography of the Arctic Ocean does more than define its shape. It sets the conditions that control ice, storms, navigation, and risk. And it explains why shifts here carry consequences far beyond the polar region. Sea ice is the defining feature of the Arctic Ocean, but it is not static. It follows a seasonal rhythm that once brought predictability to an otherwise difficult environment. Each winter, ice spread outward from the central basin and across the shallow shelves. In summer, some of it retreated, but a large portion survived year after year. This long-lasting ice acted as a stabilizing layer. It reflected sunlight, limited wave growth, and reduced the exchange of heat between the ocean and the atmosphere. That pattern has begun to break down. Ice now forms later in autumn and breaks up earlier in spring. The result is a longer open water season when wind can act directly on the ocean surface. Even when winter ice returns, it is often thinner and less durable than in the past. A key difference lies between multi-year ice and first-year ice. Older ice, built up over several seasons, was thicker and more resistant to movement. First-year ice forms quickly, fractures more easily, and drifts faster under wind and current. As the balance shifts toward younger ice, the entire surface becomes more mobile. Timing matters as much as thickness. Small shifts in freeze-up or breakup can change how much heat the ocean absorbs during summer and how much escapes in winter. Those changes affect storm behavior, wave formation, and ice recovery in the following season. Sea ice does not retreat evenly. Wind and currents create openings in some areas while compacting ice in others. This patchwork makes conditions harder to anticipate, even with modern monitoring. What appears stable on a map can change within days. For much of history, this seasonal cycle limited access and slowed exploration. Ice defined when ships could move and when they had to turn back. But even when the ice appeared to open, it never behaved the same way twice. Channels closed without warning. Flows drifted against the wind. What looked like progress one season became a dead end the next. It was this uncertainty, not distance, not cold, that shaped every early attempt to understand the Arctic Ocean. Long before satellites and forecasts, explorers were forced to confront an ocean that refused to follow patterns and resisted being mapped on human terms. For centuries, the Arctic Ocean resisted steady exploration. Progress came in short advances along its margins, shaped by ice, darkness, and narrow seasonal windows. Early attempts focused on finding passages rather than understanding the ocean itself. European explorers pushed north along familiar coastlines, hoping to reach open water beyond the ice. What they encountered instead was a moving barrier that refused to behave consistently from year to year. Unlike the Southern Ocean, where long open stretches allowed repeated voyages, Arctic exploration depended on narrow seasonal windows. Ships could advance for weeks, only to be halted or carried off course by drifting ice. Many expeditions ended not in discovery, but in retreat. In the late 16th century, Willem Barents, a Dutch navigator, pushed north in search of a route to Asia. His voyages exposed one of the Arctic Ocean's defining traits: ice that moved independently of wind and season. Ships could be trapped, crushed, or carried far from their intended course. Barents' final expedition ended with his crew stranded in the high Arctic, an early warning that this ocean would not yield easily. 2 centuries later, exploration became more systematic. William Edward Parry, a British naval officer, led expeditions into the Canadian Arctic, charting coastlines and channels that had remained uncertain. Parry demonstrated that progress was possible, but only when timing and conditions aligned. Mapping advanced slowly, measured in miles rather than breakthroughs. By the late 19th century, attention turned toward the idea of crossing the Arctic Ocean itself. One of the most ambitious attempts followed a theory that still dominated polar thinking at the time: the belief in an open polar sea. In 1879, the American expedition ship USS Jeannette entered the Arctic north of Siberia, attempting to reach the North Pole by drifting with the ice. Instead of finding open water, the ship became trapped in pack ice within weeks. For nearly 2 years, the Jeannette drifted helplessly across the Arctic Ocean, carried wherever the ice decided to move. In June 1881, as the ice pack shifted and tightened, pressure crushed the hull. The ship sank in the East Siberian Sea, leaving the crew stranded on drifting ice hundreds of miles from land. What followed was a brutal retreat across the ice and through Siberia. Many did not survive. At the time, the expedition appeared to be another Arctic failure. But 3 years later, debris from the Jeannette was discovered on the coast of Greenland, thousands of miles from where the ship had sunk. The wreckage had crossed the Arctic Ocean, embedded in drifting ice. For the first time, there was physical proof that the Arctic ice was not stationary, but part of a vast moving system transporting ice from Siberia toward the North Atlantic. The Arctic Ocean was not frozen in place. It was in motion. This discovery reshaped polar science and directly influenced later explorers. It showed that ice drift was not an anomaly, but a defining process of the Arctic Ocean itself. At the turn of the 20th century, Roald Amundsen, the Norwegian polar explorer, applied that understanding to navigation. His successful transit of the Northwest Passage confirmed that survival in the Arctic depended less on force and more on adaptation, reading ice behavior, respecting seasonal limits, and accepting delay as part of progress. Around the same period, Fridtjof Nansen, also Norwegian, took the idea further. Rather than fighting the ice, he designed a ship meant to freeze into it, allowing the vessel to drift. Nansen crossed large sections of the Arctic basin while collecting scientific data. His expedition confirmed deep water beneath the ice and mapped large-scale ice movement from within the system itself. Not all exploration relied on ships. Robert Peary, an American explorer, attempted to reach the North Pole by traveling over the ice on foot. His journeys underscored a harsh reality. At times, the Arctic Ocean was more accessible across its frozen surface than by sea. Movement of ice, not distance alone, defined success or failure. Together, these expeditions transformed blank areas on maps into partial knowledge. Coastlines became clearer. Routes were tested. But the ocean between those lines remained difficult to observe and slow to yield understanding. Exploration of the Arctic Ocean advanced through persistence rather than conquest. Each attempt reinforced the same constraint, an environment that changed faster than it could be fully measured. That constraint continues to shape navigation, risk, and loss in the Arctic Ocean today. For much of history, sea ice limited how storms interacted with the Arctic Ocean. Ice shortened the distance wind could travel across open water and absorbed much of the energy that would otherwise form large waves. This kept surface conditions relatively constrained even during severe weather. As ice coverage has declined, that restraint has weakened. Open water now appears earlier in the year and persists later into autumn. This longer exposure allows wind to act across greater distances, giving waves time to grow. Areas that once stayed protected beneath ice now experience sustained wave action, especially during late summer and early autumn storms. Storms often carry energy from lower latitudes. When they move north, they encounter sharp temperature contrasts between cold air, warmer water, and remaining ice. These contrasts increase instability. Wind transfers more energy directly into the ocean surface, and waves build faster than they once did. The interaction between waves and ice creates additional problems. Thin ice breaks more easily under wave stress, fragmenting into smaller flows that drift and collide. This process speeds ice loss and disrupts refreezing later in the season. In some cases, a single storm can undo weeks of ice growth. Conditions can also change quickly. Calm periods may give way to severe weather with little warning. Fog, snow, and darkness often accompany storms, reducing visibility. At the same time, wave energy increases. Forecasting remains difficult, particularly in regions with limited observation data. As ice retreats, the Arctic does not simply become calmer water. It becomes unstable. The combination of cold, shallow shelves, drifting ice, and growing wave energy produces a surface environment that is unstable and uneven. What appears navigable one week may become hazardous the next. These changes matter because storms and waves do more than shape the ocean itself. They define how ships move, where routes remain viable, and how quickly situations can escalate. As exposure increases, the Arctic Ocean is becoming more dynamic and more difficult to manage, setting the conditions that have challenged navigation here for centuries. Navigation in the Arctic Ocean has never followed a single reliable path. Instead, it has revolved around a few narrow routes that exist only when conditions allow and disappear when they do not. For centuries, these routes promised shortcuts. In practice, they delivered uncertainty. The best known of them is the Northwest Passage, which threads through the islands of northern Canada. Long viewed as a direct link between the Atlantic and Pacific, it tempted explorers with the idea of open water beyond the ice. What crews found instead were narrow channels, shallow depths, and ice that shifted faster than charts could keep up. Many ships reached the Arctic believing the passage was open, and learned too late that open did not mean safe. Across the opposite side of the ocean lies the Northeast Passage, running along the northern coast of Eurasia. In some seasons, it proved more navigable than its western counterpart. In others, river ice, drifting flows, and sudden freeze-up erased progress almost overnight. Timing mattered more than planning. In the Arctic, success was often decided less by distance than by timing. A third route, still discussed as a future corridor, cuts closer to the center of the ocean, known as the Transpolar Sea Route. It crosses waters that were once permanently sealed by ice. Thinning cover has made this route briefly possible in rare years, but it remains the least predictable of all. This is not a route that opens gradually. It appears suddenly and closes just as fast. What all Arctic routes share is instability. Wind can compress ice into narrow straits within hours. Currents can drive flows across channels that looked clear days earlier. Shallow shelves leave little room to maneuver when conditions deteriorate. Modern navigation tools offer better awareness, but they do not remove risk. Satellite images show where ice is, not where it will be. Even when winds ease, ice continues to drift. Decisions still rely on judgment, experience, and caution. In the Arctic, confidence offers no protection. Assumptions fail quickly. As seasonal access expands, more vessels attempt these passages. Some are built for ice, others are not. Traffic increases in routes that were never stable to begin with. These passages are often described as opening doors. In reality, they behave more like moving traps, passable for a moment, then unforgiving. Understanding how these routes function explains why navigation here has always carried elevated risk, and why the most serious losses tend to follow periods when access appears easiest. Shipwrecks in the Arctic Ocean follow a pattern. They occur where confidence meets uncertainty, where narrow routes close without warning, and where recovery is slowed by distance, ice, and time. Unlike lower latitudes, disasters here rarely unfold quickly. Ships become trapped rather than struck. Crews wait rather than flee. Ice tightens its grip over weeks or months, turning delay into destruction. Most losses happened during periods of exploration or transition, moments when routes appeared possible but remained poorly understood. Each wreck marks a lesson learned too late, recorded not in charts, but in lives and hulls left behind. Among all Arctic shipwrecks, one expedition stands apart. Not because it was the first, but because it revealed how completely the Arctic Ocean could erase certainty. In 1845, two British Royal Navy ships, HMS Erebus and HMS Terror, sailed into the Canadian Arctic in search of the Northwest Passage. They were not improvised vessels. Both were reinforced for ice, equipped with steam engines to assist sailing and stocked with provisions meant to last years. By mid-19th century standards, the expedition represented the height of naval confidence. It was also built on a fragile assumption. After entering the Arctic archipelago, the ships became trapped in pack ice near King William Island. At first, this was not unusual. Earlier expeditions had wintered in the ice and retreated when conditions eased, but this time the ice did not release them. Season after season passed, and the pack remained locked in place. The ships drifted only slightly, never far enough to escape. Pressure from the ice strained hulls and fittings. Cold intensified. Supplies diminished. What began as delay slowly turned into confinement. The failure unfolded gradually. There was no single storm, no sudden catastrophe. Instead, the Arctic imposed stillness, an environment that denied movement, resupply, and retreat. Eventually, both ships were abandoned. The crews attempted to walk south across an unfamiliar landscape of ice, water, and tundra. There were no established routes, no reliable sources of food, and no certainty that land offered safety. None survived. For more than a century, the Arctic Ocean kept the details hidden. Search parties recovered scattered traces, but the ships themselves remained lost. Only in the 21st century were the wrecks finally located. Erebus in 2014 and Terror in 2016, preserved in cold, dark water not far from where the expedition had stalled. The Franklin disaster permanently changed how the Arctic was understood. It showed that preparation alone was not enough, and that strength, technology, and discipline could not overcome ice that refused to move. Timing mattered. Ice behavior mattered. Local knowledge mattered. Most of all, it revealed a pattern that would repeat. The Franklin expedition did not fail because it was careless. It failed because the Arctic Ocean did not behave as expected. Later expeditions would arrive with better charts, stronger hulls, and modern planning, believing the lesson had been learned. The Arctic would prove that preparation still did not equal control. By the early 20th century, Arctic exploration had shifted from guesswork to planning. Ships were stronger, charts were improving, confidence had returned. The Karluk was built for that new era. In 1913, the Karluk became the flagship of the Canadian Arctic expedition. Her mission was scientific rather than exploratory, to study Arctic geography, biology, and climate. The ship entered the Beaufort Sea expecting to operate near the edge of the ice, not inside it. That expectation failed almost immediately. Within weeks, drifting pack ice surrounded the vessel and carried her westward away from her intended route. Engines could not overcome the movement of the ice. The ship was no longer navigating. It was being transported. For months, the Karluk drifted helplessly across the Arctic Ocean. Supplies dwindled. Pressure from the ice increased. In January 1914, the hull finally gave way. The ship sank, leaving the crew stranded on the ice in near total isolation. Survival depended on discipline, timing, and movement across a surface that was never still. Some crew members attempted long marches toward land. Others waited for rescue that might never come. Not all survived. The loss of the Karluk exposed a different danger than Franklin had faced. This was not an expedition halted by ice at a fixed point. It was a ship carried far beyond control across an ocean that ignored intention entirely. The Arctic Ocean did not block the Karluk. It moved her. The lesson was clear. Even modern ships could be reduced to passengers once ice decided the direction. And in the decades that followed, other vessels would enter the Arctic, believing design alone could overcome that risk. The Karluk was taken by drifting ice far from land. The next ship was built specifically to work with the Arctic and still failed. If any ship was designed to succeed in the Arctic Ocean, it was the Maud. Commissioned by Roald Amundsen, the Norwegian explorer whose experience in polar regions was unmatched. The Maud was purpose-built to endure ice pressure rather than fight it. Her hull was shaped to rise when squeezed, reducing the risk of being crushed. She represented the most advanced Arctic ship of her time. The plan was ambitious: to drift with the ice across the Arctic Ocean while collecting scientific data, improving on earlier attempts to understand ice movement and ocean currents. For years, the Maud survived conditions that had destroyed other vessels. She endured long winters locked in ice, continued drifting when engines were useless, and completed sections of the Northeast Passage that had defeated earlier expeditions. But endurance did not equal permanence. By 1930, after years of service in Arctic waters, the Maud was worn down not by a single storm or ice event, but by cumulative strain. While operating near what is now Cambridge Bay, water entered the hull faster than repairs could contain. The ship was abandoned and slowly sank in shallow Arctic waters. No lives were lost, but the message was unmistakable. Even the most carefully designed vessel could not remain indefinitely in an environment that applied pressure year after year. Survival was possible, control was not. For decades, the Maud remained where she fell, preserved by cold water and isolation. In 2018, her remains were finally recovered and transported, a rare case of an Arctic shipwreck returning from the ocean that claimed it. The Maud proved that adaptation could delay loss, but not always prevent it. The Maud endured by adapting to the Arctic rather than fighting it. Other vessels would leave the ice behind altogether and still fail to escape its reach. Not every Arctic shipwreck ended in destruction. Some simply refused to end at all. In the autumn of 1931, the SS Baichimo, a steel-hulled cargo steamer operated by the Hudson's Bay Company, was completing a routine trading run along Alaska's northern coast. She was not an exploration vessel or a risky experiment. She was a working ship built to supply remote Arctic communities and returned south with a cargo of fur. On October 1st, as winter tightened its grip, the Baichimo became trapped in pack ice near the coast. At first, the situation did not seem unusual. The crew crossed roughly half a mile of ice to reach the town of Barrow, taking shelter for 2 days while waiting for conditions to improve. When they returned, the ship had broken free. For a moment, it appeared the Arctic had relented, but the reprieve was brief. On October 8th, the ice closed in again, this time more thoroughly. Movement stopped, pressure increased. With freeze-up advancing, the Hudson's Bay Company made a decision. On October 15th, aircraft were dispatched to evacuate most of the crew. 22 men were flown out. 15 remained behind. Those who stayed constructed a wooden shelter some distance from the ship, intending to wait out the winter if necessary. The Baichimo still stood intact in the ice, her hull holding firm. There was no dramatic failure, just waiting. Then, on November 24th, a powerful Arctic blizzard swept through the area. When it passed, the ship was gone. From the shelter, there was no wreckage, no fragments in the ice, no sign she had survived. The skipper concluded the storm had finally broken her apart and sent her to the seafloor. Days later, that assumption collapsed. An Inupiat seal hunter arrived with unexpected news. He had seen the Baichimo intact, drifting roughly 45 miles away. The crew tracked her down. Faced with the reality of an unmanned ship drifting freely into winter, they made a final decision. Believing she would not survive the season, they retrieved the most valuable furs from the hold for air transport. With that, the Baichimo was abandoned for the last time. The Arctic did not accept the conclusion. Weeks later, the ship was sighted again, adrift, unmanned, and stubbornly afloat. Over the following years, she appeared across vast stretches of Arctic waters. Whalers, traders, and coastal communities reported her lodged in pack ice, then later drifting through open leads. Some crews attempted to board her. Others were driven off by weather, ice movement, or sudden storms. Then she would disappear and return. For decades, the Baichimo surfaced without warning, earning her reputation as the Arctic's ghost ship. She followed no route and answered no intention. Currents carried her. Ice released and reclaimed her. Seasonal cycles moved her across a landscape that remained largely unobserved. At some point, sightings ceased. Whether she finally sank, broke apart, or lies preserved in shallow Arctic waters remains unknown. What the Baichimo revealed was not the strength of the ship, but the indifference of the ocean itself. The Arctic Ocean did not hurry her destruction, nor protect her survival. It simply continued operating on its own terms. Ice formed and fractured. Currents flowed, seasons repeated. Human presence had exited the story. The Baichimo was not shaped by urgency, ambition, or survival. She was shaped by the same systems that govern everything else in these waters. And those systems do not only determine the fate of ships, they shape where life persists, how ecosystems function, and why the Arctic Ocean remains one of the most delicately balanced and unforgiving marine environments on Earth. Beneath the ice and storms, the Arctic Ocean supports a food web built around extreme limits. Life here survives not through abundance, but through precision, timing, movement, feeding, and breeding around narrow seasonal windows. Sea ice sits at the center of this system. Along its underside, algae grow in thin layers, forming the foundation of the Arctic marine food chain. When the ice retreats in spring and summer, that energy moves upward into zooplankton, fish, and eventually into the region's most recognizable animals. Polar bears rely on the ice as a hunting platform. They wait beside breathing holes to catch seals, using the ice not as shelter, but as access to food. When ice forms later or breaks earlier, hunting seasons shorten, forcing longer swims and greater energy loss. Along the same ice edges, walrus gather in large numbers, using the pack as a resting platform between dives. They feed on clams and other organisms on the shallow seafloor, linking surface ice conditions directly to life below. As ice retreats farther offshore, walrus are increasingly pushed onto land, changing long-established patterns. In open water and along coastal routes, beluga whales move through the Arctic Ocean in seasonal migrations. They rely on sound more than sight, navigating and hunting in dark ice-covered waters. Changes in ice cover and shipping noise alter how these whales travel and communicate. Other marine mammals follow similar rhythms. Narwhals, closely tied to dense pack ice, remain among the most ice-dependent whales on Earth. Bowhead whales, adapted to break ice with reinforced skulls, move slowly through Arctic waters, feeding on plankton during brief periods of abundance. Fish and smaller organisms form the connective tissue of the ecosystem. Arctic cod, a key species, links plankton to larger predators. Its distribution shifts with temperature and ice conditions, influencing everything above it in the food web. Seabirds arrive in vast numbers during summer, nesting along Arctic coastlines and feeding offshore. Their presence marks the short period when the ocean produces enough energy to support life at scale. This entire system operates close to threshold. A few weeks' change in ice formation or melt can reshape where animals feed, rest, and migrate. Stability depends not on strength, but on predictability. As ice patterns shift, the ecosystem changes form, affecting each species differently. The consequences of that reorganization extend far beyond wildlife alone. Because the Arctic Ocean does not only support life here, it helps regulate systems that reach much farther south. The Arctic Ocean influences the planet far beyond its size. Though it is the smallest ocean on Earth, it plays a critical role in how heat, energy, and circulation move through the global system. At the center of that role is ice. Sea ice acts as a reflective surface, bouncing sunlight back into space and limiting how much heat the ocean absorbs. When ice cover is extensive, the Arctic helps cool the planet. When ice retreats, darker water absorbs more solar energy, reinforcing warming rather than resisting it. The effects of this feedback extend far beyond the Arctic. As the Arctic Ocean warms, it affects how water moves between oceans. Cold, dense water formed in polar regions contributes to large-scale circulation patterns that help regulate temperatures across the Atlantic and beyond. Changes in temperature and salinity in Arctic waters can weaken or alter these flows, influencing weather far from the polar circle. Freshwater plays a role as well. Rivers from North America and Eurasia pour enormous volumes into the Arctic Ocean. When ice melts more rapidly, additional fresh water spreads across the surface, changing density and stratification. This can reduce vertical mixing, trapping heat near the surface while limiting nutrient exchange below. The atmosphere responds in parallel. Reduced ice cover alters temperature contrasts between the Arctic and lower latitudes. These contrasts help drive wind patterns, including the jet stream. When they weaken, weather systems can slow or stall, increasing the likelihood of prolonged heat, cold, or precipitation events elsewhere. The Arctic Ocean also functions as an early indicator. Changes appear here sooner and more clearly than in most other marine regions. What unfolds in these waters often foreshadows broader shifts that emerge later at lower latitudes. These forces are linked. Ice, water, air, and biology push on each other constantly. A change in one element feeds into the others, amplifying effects across systems rather than remaining contained. This imbalance is what gives the Arctic Ocean its outsized importance. Its influence is not measured in size, but in leverage. Understanding how this ocean works helps explain why changes here attract global attention and why decisions made far from the Arctic still shape its future. The Arctic Ocean is no longer shaped primarily by isolation. Today, it is shaped by interaction, climate systems, shipping networks, and decisions made far beyond the polar circle. Sea ice continues to thin and retreat, altering when and where the ocean is accessible. Seasons that were once defined by long closures now include brief periods of exposure. These changes do not follow a straight line. Some years reverse earlier patterns, others accelerate them. Variability rather than consistency has become the defining feature. As access increases, activity follows. Shipping, research, and monitoring expand cautiously into waters that were once unreachable. Each arrival brings new data, but also new pressure. Noise, fuel use, and the risk of accidents rise in environments where response options remain limited. At the same time, the Arctic Ocean is becoming more closely observed than ever before. Satellites track ice movement daily. Autonomous instruments record temperature, salinity, and currents beneath the surface. This growing network has improved understanding, but it has not simplified the system being measured. Uncertainty has become the defining condition. Ecosystems adjust unevenly. Some species expand into newly suitable waters. Others retreat as familiar conditions disappear. These shifts ripple outward, affecting food webs, migration routes, and coastal communities that depend on predictability rather than abundance. The Arctic Ocean's future will not be defined by a single outcome. It will be shaped by balance between access and restraint, observation and intervention, short-term opportunity and long-term consequence. What happens here matters because of scale and position. This ocean influences climate, circulation, and biological systems that extend far beyond the Arctic itself. Small changes carry outsized effects. The Arctic Ocean does not dominate the planet by size. It matters because of how tightly it connects everything else. The Arctic Ocean matters not because of its size, but because of its position. It sits at the intersection of climate, circulation, and life, regulating heat, shaping weather, and supporting ecosystems that operate within the narrowest margins on Earth. Small changes here do not stay small. They spread outward, influencing oceans, atmospheres, and coastlines far beyond the polar circle. History shows that this ocean has always resisted control. Explorers struggled to map it. Ships were lost despite preparation and design. Even today, access remains conditional, shaped by ice, storms, and uncertainty rather than intention. What has changed is not the Arctic Ocean itself, but how closely it is now connected to the rest of the world. As ice patterns shift and observation increases, this ocean reveals its role more clearly. It reflects sunlight, moves fresh water, drives circulation, and signals change earlier than almost anywhere else on the planet. Decisions made thousands of miles away now register here first. That is why the Arctic Ocean matters most, not because it is remote or difficult or extreme, but because it quietly shapes systems far beyond its ice-covered boundaries. Its influence moves through ocean currents and atmosphere, often unnoticed. What happens here unfolds slowly, but it does not stay contained. The signals travel outward long after the ice has shifted and the storms have passed. And as the Arctic Ocean continues to change, it remains a place that demands attention, not for what it offers, but for what it governs.